Good day. Welcome to this week's installment of the video lectures for Computer Science 114. So last week we discussed data types, chapter 3, and the topic for today is then creating data types. So I'm going to go a bit back on the work that we've done last week. So last week basically I have started and discussing data types. So we said that there was a need for a data type to exist, that we want to augment the language that we currently have. Remember that a data type was then defined at this point as a set of values and operations on those values. And you have known data types from the very beginning when you started with Java programming. You've been using it all along. So the example that I have there on the slide are the basic types that we had. So I had the Boolean there, an int and a string. So in other words, we have a certain data type that has a name. Then a data type can take certain values. So for example, a Boolean can have the values true and false. An integer, of course, have integer values ranging from the least negative number to the most positive number. And then for a string, for example, it's all the possible of Unicode characters that you have. Also in a data type, you have certain operations that you can do. So for example, on a Boolean, you can apply a not operator, you can do an and between two Boolean values. If you work with integers, of course, you can do addition, the normal things that you know about integer work, multiplication, division, all those things. And with strings, we have different kinds of operators like to concatenate things, to compare strings. And in fact, last week we have been spending a lot of time using all these things. So the aim of last week's lectures was to show that you can use data types without actually knowing how it was implemented. So you can just use them there. If someone else has implemented them, I've mentioned that, so basically you have a library of code available that you can use, that someone implemented, and then you write client code that will use these data types. Now this week, of course, we want to go now a step further, and you will create your own data types. And this is thus the theme for this lecture today. As in the case, I should just motivate another time why we need data types. So on the screen there I have the Boolean, the int and the string, but you could of course imagine that you have all sort of different programs that you would like to use. For example, we have had in the class discussions about using pictures, about strings, and so you basically want to make the language bigger by having your own data types, and that's the reason why we're doing it. Now in Java, we want to define data types. And again, I have emphasized this many times and I'm going to say it again. So a data type is a set of values. So with a data type, you associate certain values and then you have operations defined on these values. And that's what we want to do. Now in Java, when we use data types, the concept or the part of Java that allows you to create data types are the class. So in Java, if you write a class, you are basically defining a data type. And for a class to work, you need three things. You have the instance variables there, you have the methods that you can define, and then you have constructors, that is to create new instances of this class. So your instances are in fact the instance variables are the set of values that you have. That's the data, the underlying data of your data type. Then the methods are the operations on that. So plus minus in the case of integers, but of course we have more advanced data types at this point. So now you will define your own methods, your own operations on these things. And then finally constructors are this way of creating, of instantiating an object. Now as with all these things, I'm going to use an example to discuss data types, how to create them, and we are going to do that at the hand of several examples today that will hopefully illustrate all these things. So the example that we have over here is that we want to create a data type that manipulate point charges. Now you can imagine that we have here on the screen, we have here a particle, a point charge, and it is associated with a certain charge on it. And then what we're interested in is what is the potential at different points due to this charge. And without going in all the details, since I mean this is now actually in a completely different field that this problem exists, but there is this formula over there that relates how the potential is changing given due to this charge. So let's go through this again. So basically, if I have a charge over there at point xy, then the potential at this point xy, an arbitrary point xy, is then related to k. K is just the constant, the electrostatic constant, and then q is the charge of this particle, and then r is the distance from this particle to where I'm interested in what the charge, the potential is over there. And so if you plug in all these numbers, you can have the potential over there. So in other words, we want to model this. We want to get right that we want to work with point charges, and we want to abstract the concept of a point charge in our program. So for that, we have to do a couple of operations. So what do we need? Well, we want to create a new point charge. And of course, to create a new point charge, we need the position where it is. So in this case, it will be Rx, Ry. We also have then the electric charge associated with that particular point charge. And then we also want to be able to calculate for a particular point charge, we want to calculate the electric potential at that point. So that's the one thing we want to do. And then finally what we want to do is we want to convert this point charge to a string. So those are the operations that we want to be able to do. So what I'm going to do now is I'm going to show then this is a bit more concrete. So we're going to write down an application programmer's interface, an API for this operation. So again, the goal stays the same. We want to create a point data type to manipulate point charges, and we have a set of values, and that are the three real numbers that specify the position and the electric charge. And then of course we have the API, and the API I have over there. So I have a constructor to create a charge. I have the potential that I want to calculate. So given a point x, given a point y, I want to calculate the potential associated with this charge, and I want to convert the charge to a string representation. Now let's assume that this was implemented already, like we did last week. So someone, I don't know where it's coming from, some mysterious person maybe implemented this for you and gave you the source code for charge. So once you have that, you can start using it already without knowing how it was implemented. It's important, we've emphasized this many times last week. You can use a library without knowing how it was implemented. And so here I have a little program that is a client program that uses this charge that that I've described. So let's go through this line by line. So what I do is I read in the x value and the y value. Let me see what they are doing. So that is where I want to know the potential at. So that you can imagine that I type in, I want to know the potential at position x and position y. Well, at position x, y in the Cartesian plane. And then I have two charges. So I have charge C1, and I create a new charge. And remember, that's the x position where this charge is, that's the y position where the charge is, and that's the actual charge. I create a second one. And this again, we've done this last time, but it's important to realize this now at this point. So given C1 that I have, this object that I have over there, with C1 is associated a particular xy position as well as a charge value. And when I calculate C1 dot potential at xy, and xy is the numbers that the user has entered, then I calculate the charge for the value associated for the charge associated with those three values. When I do then C2 dot potential at, then I calculate the charge associated with this particular particle. And of course, once I have calculated the two of them, I can print them out. And remember, if I say standard out of print line C1, then if I print out a string, then Java will automatically call the .toString function to print this out, to convert the object to a string representation. And then of course the charge at position xy is the sum of all the charges of all the particles that act on that point. So that's more or less the client code that we want to use. So this should not be something new to you at this point. This is just how we can use something that someone else has implemented for you. But now we want to go one step further and we want to implement this. So I want to write the charge. And I'm trying to do this while you are here. So I'm going to get back to the API again. Let me just get the right slide. So there is the API, and I'm going to write code now to implement this API, since that is a starting point. The application programmer's interface is sort of a contract. It's an agreement between the person providing the library to the client, say, I will implement these things, and when you call these things, I will behave in a certain way. So let me just open the text editor here, and then I have it there. So I'm going to try to have the PowerPoint there, you can see it, as well as having the text editor here. Hopefully you can see everything. So to write a new data type, you use, of course, write a Java class. So public class charge. And I'm going to save this. As always, you save this as charge.java. And there I have it. Now, the first thing I'm going to create is the data associated with this particular class. Remember, I said a data type has the components of there's the data associated with the operations, and then there is also the constructors. That is how you would create the actual objects of that, the instances. Now, for a charge, we need three values. We need the xy position where the particle is located, and then the actual charge. So to do that, we write down private final double, and I'll explain that right now. So Rx is the x position of the charge, Ry is the y position of where this particle is, and they are of type double, so we assume that they can be anywhere. Now private, we will discuss that in detail next week. For the moment, you should just remember that when a thing is private, then it's only visible within the class that it was defined. So for example, in this case, charge, in this class, Rx and Ry will only be visible within the charge class, and no client code can use this. As a rule of thumb, you should always make your instance variables should always be private, unless you can think of a very good reason, and I think if you enumerate all the reasons, the first 10 reasons will be invalid. So if you have then another reason on top of that, then you can make it non-private. Final means that once we've given a value to x and y, it cannot change. Again, we will discuss more of the design next week when we have a more discussed design of APIs. For the moment, just know what it is doing. And then of course the other thing that we need is of course the charge associated with this particular charge, this particle that I'm working with. Now at this point I have the data associated with my charge. The next thing I want to add is the constructor. So remember, the purpose of the constructor is to create an object of this particular type of, so an instance of this particular class. So again, I have public charge, and so it looks almost like a normal a method or a function that you've written before, with slight changes. The first thing is we don't have any return type there. Well, in a sense, charge is the return type. And then I can give argument values to it. So I can give x, maybe x0, double x, y0, and double q0. So those are the values that come from the client that using charge. They will set those values. And now using that, I'm going to define a new class. Charge. So let's write the code for that as well. So in this case, what I want to have is that Rx, the x value associated with this charge should be x0, the y value of this position of this charge should be y0, and then the charge should be q0. And look here what we're doing now. There's two types of variables here at play. So we have the argument values, and those are just the normal values, parameters that you passed and you used to them. You've used them in the previous semester. What's interesting here are these other variables that I have there, the instance variables that are associated with this particular class. So now I can write, if I have a client code here, this is not part of this code, so this is just if I have a client program somewhere here, I could write things such as charge C1 equals new charge, and then I can give values here 0.5, maybe 0.6, and I don't know, 1. And remember now, when I do this, it calls the constructor over there automatically. So in other words, C1 has now these instance variables Rx, Ry, and Q, and they are associated with this object. And if I make another one, charge C2, I can create a new object, and they can be completely different values, maybe 0.72 for that matter. Okay, so this is then how I would use this particular thing. Okay, so now I have the instance variables, in other words, the data that's associated with the data type. I also have a constructor, so I can construct it, and now I must implement the operations. If I go back to my slides, you will see there that I have let me just wait for this thing to come up. Yeah, there it is. So I have the charge, the constructor, I have the data associated with it, and now I have to implement the operations. I'm just going to go a bit forward. So I've shown you, these are just also in the slides. These demonstrate the instance variables. I show you the constructor. And rather than writing the instance method myself here live, I'm going to go through the example that I have over here. So I want to calculate the potential at function. Remember, what does potential at? Calculates the potential at the point xy given a particular charge. And how do you write such an instance method? It's very similar to the static methods that you've implemented before, with the exception we don't use the word static there. But it's also a lot different if the word static is not there, since now we have access to all the instance variables associated with this particular object. So let's go through it. Public means it's accessible from client code. So the convention is that the things that you make available for other people, for clients to use, they should be public, and all other helper methods should be private. Double is the return type. In this case, the charge will return a double. And then I have the method name potential at, and that is just the name of it, and then I have the argument values. Now, I go through the code to do this. Of course, I need the K, that's the electrostatic constant, and then I just calculate the formula. So in other words, I calculate the distance from the charge position, the particle's position, to this xy position. In your free time, maybe you should go and make sure that you understand that the calculation is correct. It is correct. The things I want to highlight is the following. So there are three kinds of variables now at play here. So I have the argument values, the parameters that I've passed. I declare some local variables, they are over there, and then there are these instance variables. And note that these instance variables are associated with a particular class, particular object, not class, particular object. So this Rx and Ry. So if I have, for example, remember I've created on the previous slide, I can show you maybe, I've created charge C1 that has values associated with it, and I have charge C2 with values associated with it. If I now write down double V1 is equal to C1 dot potential at, then basically what it means is that I'm going to calculate for a particular charge particle, in other words for this one, with this xy position, this charge, I'm going to calculate at this xy position the potential. Similarly, if it is this one, I use actually the xy, the position of this charge, and then the associated electric charge of that. And so this is how we define then the instance variables, the instance methods. And then here on the screen is now just a listing of the complete class with all the things there. There's the method to string, and that will basically convert a charge to a string, but it should not be difficult to see this code. As homework, you should go and sit down and make sure that you can read all these lines. So at this point, I think we should just summarize what I have at this point. So I've created a new data type. The purpose of this data type was to encapsulate the idea of a charge. So for a particular xy position and a particular charge associated at that position, I can calculate things such as the potential for an arbitrary xy point, and I can also get a string representation of this class. I've mentioned the three components that I need. I need constructors to create the class. I also have instance variables, and I also have then the instance methods that I'm going to use. And with these things, you have everything to be able to write your own data types in the future. Just an example, what one can do is actually visualize, let me just see, one can visualize the charge of the electric potential of a set of points like this due to many particles in there. So assume that I have, for example, 10 particles over here, or n of them, n point charges sitting there. Then of course, if I'm at this point, then I will have a potential because of each of these n point charges. And so basically I have to do the sum over all these point charges to calculate the potential at this particular point. So I want to write a little program that can do that. Now, how will this work? Well, in a file, say charges.txt, we can then write, define how many particles are there, how many charges are there, and then for each one of them, I'm going to specify its x and y position as well as the charge associated with that. And then I'm going to, for a particular grid, I'm going to calculate the potentials at all these things. I'm just going to see if I have an example here. Once it's implemented, that it work. So if you run this, you will get something such as the visualization that I have over there. So just to make sure that you understand what I'm doing, just reiterate over things. So I have this file charges.txt. They contain all the particles, in this case 9 of them, and with the charge at each point. And then I want to visualize for all this point in this grid then what the potential is. And so let's write some code to do so. and I have it over here. So the first thing that we want to have over there is that we want to have not a single charge at this point, but we actually want to have multiple charges. And I don't know at the beginning how many charge objects I need. So I probably need 5 or 10 or 9 in this case as an example that I have over there. Now if you remember back to the previous semester, the semester 1 in Computer Science 114, you've learned about something to handle those cases where you want to have many variables of the same type. You don't know how many are there, and you want to use them and to work with them, and of course you use an array for that. Now in the case of the normal array, well, it's always an array. In the case of what you've done the first semester, the arrays were usually of primitive types like an int or a string or whatever you've used so far. But there's no reason that an array can't be of a data type that you've defined. And so in this case, what I want to create is an array of n charges. So I read at this line, I read in the charge, the number of charges that I will have, in this case 9, and then I'm going to create an array of 9 charges. Now you should be careful when you look at this code, since what I have over there is that I use new to create the array, so I allocate memory for the array, but not for the actual objects stored within the array. So what I have then next is I read this file line by line. So there are 9 lines. I get the x position, the y position, and the charge, and then I create a new instance of a charge, and then this charge is then associated with this particular and I store it then at this position. So it's important that you understand this. Maybe I should try to draw this on the board just to make sure that you understand this. So you can imagine that I have here an array, and at each position in this array I have a reference to a charge. So these are the charges array. I think I called it A. So this is A. Now when I say new charge and then n, I basically allocate this array. So remember, if you have the picture correctly, somewhere in memory you have the variable a sitting there, and if I have new charge, you can imagine that it returns a reference to where all these things are. But now I just have, at this array I can only store references to charges. So when I read in a line of code such as if I have an x0, a y0, and a q0, then I have to store, and I make a new charge with x0, y0, q0. Basically somewhere else in memory I will store a charge object. So assume it's stored like x0, y0, and q0 in memory, and this will return, this new will give me a reference to this, and when I say a0 for example equals this thing, then the result is that this new operation will return the reference to this place, and it will be written over there. So just to summarize again, we have thus two things going on there. We have allocation for the array, and then the second thing that we have is that we create the actual objects. Something that you can go and try out is to actually go and remove this new statement over there, and then maybe try to print out the values, and then you will get something such as null pointer exception, since these things don't exist. Try to do the incorrect things and then see what will happen. Okay, now once I've done all these things, I can actually go and calculate the potential at the initial problem, solve that. Remember, the initial problem is I give you a grid of points, and then you want to calculate at each point the potential due to all the charges that I have over there. So I make a new picture. This should not be a problem for you anymore. I go through all the points in this grid. So the eyes go the rows and the columns, and then for a particular point I have to calculate the sum of all the charges associated with acting on that point. So of course the potentials start at 0. I go through the n charges I have, so for k go from k0 to the n that I have, and then this is just a bit of scaling, and I calculate the potential at position x, y associated with this particular particle. Remember this array. Let me go back. This array is an array of charges. So when I write AK, I basically get back a charge object. And so in other words, on that I can then use the potential at function to calculate the potential at that xy position. I add it to the potentials that I've calculated so far, and then I just display it. Take note of this thing over there that I have to flip the coordinates. Remember that in the case of an image, the coordinate 0, 0 is the top left corner, but in the case of the xy Cartesian plane and how this charge is defined, then the xy position 0, 0 is actually at this point. Now this page just looked like my blackboard is usually looking full of messy stuff, so I'll just throw it away. I think we should install this in the lecture halls, that I can just throw away what I've written. Good. Okay, so now I'm basically finished this example of a charge, how it's working, and if there's any questions regarding that, please feel free to ask them on piazza.com. So what I want to do next is I want to discuss another application for another example, and this is within the domain of turtle graphics. Turtle graphics is quite an old concept that has been used, and the idea is that you have a turtle, and the turtle can be at a certain position and it's looking in a certain direction. And then this turtle can do two things. It can move to another point that you specify for a certain distance, and while it's moving to this point, it will draw a line. Or you can instruct the turtle to turn around and look in another direction. And those are the two things that you can do with a turtle. And so if we look at this, I have therefore I just need water, so you probably haven't seen that part. It's a nice thing about cameras. So I have the turtle graphics API that I have over there. Again, what's the goal? The goal is to create a data type to manipulate a purple turtle moving in the plane. Those of you who were in my lecture on Friday morning will remember that I said that one should always answer 3 questions: what, why, and how. So what do I want to do, why do I want to do it, and how do I want to do it? And you will see that this convention is also followed in this book. So the goal is usually what do I want to do, why is usually because it's nice or because it has some nice applications, this particular problem, and then the how is when we go and actually implement the API. So get back to my example over there. So I have the API. So I have a class turtle and I can construct it. And how do I construct it? Well, I tell the turtle the initial position where it is. So in other words, at position x0, y0, and with a certain angle. And this angle is from counterclockwise from the x-axis. And then, as I said before, the turtle has 2 operations. It can either turn left with a certain number of degrees, or it can go forward, and as it goes forward it will draw a line. So for example, here's code to draw a square. So I make a turtle at position 0, 0, 0, so it's facing nowhere. Well, it's at the origin and it's facing at 0 degrees. And then I say go forward 1. So if I can maybe draw this again, so if this is my xy plane, so this is position 0, 0, and it's facing in this direction, so that's 0. Then I say go forward, and then I tell it go left, turn left, and so it goes left, and so I draw this square that I draw. So this is how you would operate this. You could think that, I mean, this is now a bit of pointless to play around with turtles, and I mean, there's not even a hair at this point. But turtle graphics is actually quite important, and I will show a little bit of example here, but it's important that you actually go in the textbook and read a bit more about that, and you will see that turtle graphics are actually used quite, have some very nice applications, apart from just drawing this square that I show over there. Okay, so let's get back to this. So again, I have a class, that's how I implement a data type. With a turtle, I have the X, Y position associated, as well as the direction that it's facing. Now I have to do all these things. So remember I said we need the instance variables, we need a constructor, and then we have the operations defined in it. So I have the instance variables here, that is the X, Y position, the angle, and look carefully there. What I do, I say that the X position is associated with this X1 0 that the user provides, Y, and then also the angle. And then I have the operation turn left, and it's really easy to implement. Basically I just add the number of degrees to the current angle that I have. Note though that I have two variables here at play again, the instance variable angle, as well as the delta, that is the number of degrees it should turn, specified by the client code. And then I have go forward. What I do is I have the old X and Y position, where I start, and then the next X, Y position I can get with trigonometry. So if this D is the distance, that the step size, then of course the new X position will be just the cos of this angle that it's currently facing, so the d cos of alpha, and the Y position will just be the sine of d of this angle multiplied by d, and that is how you will get the new X, Y position. So we start off with an old with an X, Y position, we call it now old X, old Y. We calculate the new X, Y position due to the step size that I'm going to use, and then the current orientation of the turtle, and then I just draw a line from the old X, Y position to the new X, Y position. And then I have an example over there that will actually use this some client code. So here I want to do polygons. So as a user you would specify the number of angles that the polygon should have. So if it's 3, of course, it's a triangle. 7, it's now I can't remember the name of it, a heptagon, I think it should be something like that. And then if you specify many angles, like 1000, that's a good approximation for the circle. So of course we have the number of angles specified by the user, then the size of the angle. Hopefully you can still remember that for a polygon of with n angles, the size of these angles should be 360 over n. This I leave as homework. How to prove that the step size should be the sine of the angle over 2. Remember that in Java the sine function actually works with radians, and we specify the radians in degrees, so we just convert the degrees to radians and then use the sine on that. And then I have a turtle starting at a particular point, and then for the n sides of this polygon that I draw, I go forward and I turn, I go forward and I turn. If I do it many times, I get this kind of shapes. Interestingly enough, there is something called spira mirabilis, and that's a very old thing that appeared many years ago. I can't remember the exact date when they discovered. In any case, but you could imagine you have a turtle that is kind of getting tired. So it moves around, but as it moves around, it's not moving the complete step size that you specified, but it's always making it a bit shorter. So it started off maybe with a step size of 1, and then it makes it shorter and shorter and shorter and so forth. And so let's implement this. So we have this decay factor that you specify, how lazy the turtle should get over time. And the rest of the code is the same, except with the exception there that I have now the step size, I divide it by decay. So I make the step size every time a bit smaller. And when you do that, you get all these interesting spirals, the so-called logarithmic spirals or spira mirabilis. And they look kind of cute. And apart from that, the interesting about them is that they appear in many places in nature. For example, here they are in a storm. You can see them. There is some animal and there's a galaxy, and they appear everywhere. And I encourage you to read a bit more about them when you see them. Here I've just written code that would be able to draw them using turtle graphics. Now at this point, I think you should be able to create data types and make your new ones. I've discussed it at the end of two examples, the one being the charges that I have, and also at the end of turtle graphics. In the next lecture that I will present, I will create another type of examples. I will do more examples showing how you can create your own data types. Thanks very much.